In 7.2, we're going to be going into logarithmic functions. In the previous section, we went through exponentials, and now what we're going to be doing is building onto that with its closely related logarithmic functions. So first we need to review what exactly logarithmic functions do again, and then also learn how to graph them, just like we were learning how to graph the exponentials. Just a quick review about what inverse functions are. This is the algebraic definition. And basically, if you take a composition of two functions and they equal x, that's when you know you are going to have an inverse operation relationship. So here's an example. Obviously we know that multiplication, as we can see here, and division undo each other, so they're inverses of each other. But just to kind of see exactly applying it to this definition, if I were to take f of g of x, what I would be doing is I would be putting this g of x function into my f of x function. So I'm going to go ahead and say f of x divided by 4, and when I actually take that and plug that into my f function, I would get, and what we can know here is if you ever took 4 times x divided by 4, they would undo each other, we would get x. That's something that we're pretty comfortable with. And I am going to bring back my robot from last year, just because he's the best way I know how to tell you about these inverse relationships. So here we have a robot and we have the function x squared, so I'll write that here. Alright, and so what he does, he's a machine that will produce any kind of number that's inputted into him. He will produce something that's squared. Okay, so there's that. And then once again what we have are these inverse functions. So here's our x squared. That 64 that he did have, took that input of 8 and squared it, he got 64, and then what the inverse function would do is he would take that output of our original function, and what that inverse function would do is take that in as his input and then produce what we began with. So I guess much to the x squared function's dismay, what we get is his work undone. This is my best explanation for why the x and y roles are switched. So if you did have something like this, I'm going to fill out this table, and we had 8 squared, it would be 64, or we had 2 and that was squared, we would get 4, or we had 1, I don't know, I'm just picking random x's at this point. So that's why we do this whole thing, because in comes this inverse function, and it would take all those inputs and swap them. Take an original function and then take the inverse function and just reverse those xy roles. So be specific with what this section is dealing with. Now that we're talking about logarithms and exponentials, know that they are inverses of each other. Okay, and just as we're able to write any kind of multiplication problem, so for example 4x is equal to 16, we could take this and rewrite it as a division problem by just doing the inverse, x equals 16 divided by 4. So we took this multiplication equation and wrote it as a division equation. What we need to be able to do is write logarithms as exponential equations, and vice versa. So take an exponential and write it as a logarithm. So here's an example. I'm going to do number 2 from your homework. Okay, all these ask us to do is write the logarithmic equation as an exponential in exponential form. So here I have a logarithmic equation, and just like I would have had this multiplication equation, and what I did was rewrite it in the form of division, I can do that here. I have this logarithmic equation, and it is a base 3 log, so I can use an exponential base 3 to undo it. So I'm going to actually write this as an exponential base 3. This becomes an exponent. Same with this. So I have 3 to the 4. These would cancel each other out because they're inverse functions, and I'd get 81 is equal to 3 to the 4. And that's a true statement right there. Number 10, we're going to be taking that same idea, but this time we're going to start out with an exponential. So we just need to write this as a logarithmic equation. So I'm just going to see, here I have this exponent, or I'm sorry, this exponential, or this power, base 8. So I'm going to find or use the log base 8 to undo an exponential base 8. So whatever you do to one side, you also have to do the other. So I'm going to be able to cancel those out. A log base 8 will undo an exponential base 8, and we would get 2 is equal to log base 8 of 64. Done. Okay, so there is how you would rewrite them back and forth. Number 20 is slightly different because we're actually going to be solving a logarithmic equation. And to do that, we're going to rewrite it as an exponential. So number 20, we have this expression, sorry I said equation earlier, we have this expression, a log base 2 of 1 over 8, and I am going to turn this into equation and just write this as equal to x. This logarithmic expression is equal to some number, and I'm going to try to solve for it right now. So what I can do is, we're not as familiar with this notation, so logarithms are somewhat hard for us to just kind of comprehend when we're looking at them like this. But if I can turn it into an exponential, it might be able to help us. So I'm going to go ahead and say this is the log base 2. I could undo it with an exponential base 2. So I'm going to take a base 2 to both sides. Those cancel each other out. This exponent is going to become grounded. I get 1/8 is equal to 2 to the x. This is where we're going to have to use some of those exponential properties from the last PowerPoint. It was the last slide that I showed, so if you need to go back to that, do that. But I'm going to start to try to see, well, I have this 2 and this 8, and we're going to do everything in our power to make them so that they have the same common base. So I'm going to rewrite this as 1 over. I do know that I could rewrite 8 as a base 2 exponential, or as a base 2 power, so I'm going to rewrite this as 2 to the third equals 2 to the x. Alright, here's where our property was going to come into play because I have this common base now. I just need to get this as to be the top, so to be on the top, so I'm going to rewrite it as cross the line, change the sign, 2 to the negative 3 equals 2 to the x. So therefore, I mean, the only possibility for x is to be negative 3. So our final answer here is going to be negative 3. X is equal to negative 3. So this logarithm can be simplified to be negative 3. Okay, so that's what we're doing with our logarithms and exponentials. We're relating them to each other. Another part of this section is to be able to graph a logarithm. So when I'm graphing logarithms, what I'm going to go ahead and do is look at this equation, this basic logarithm. And you can compare this to my last PowerPoint about graphing exponentials. What we graphed was y equals 2 to the x. So we specifically graphed the inverse operation, the most basic inverse operation of a log base 2 of x in the last PowerPoint. But what we're actually going to have to do is, because this is kind of hard for us to get a handle on, what we actually do is we graph the exponential function related to this. So I'm going to go ahead and make the table, my xy table, and then we're going to graph this just like normal. I'm going to plug in my negative 1 for sure, the 0, 1, and maybe even 2. You don't always have to go to 2 because you know the basic shape. But then I'm going to go ahead and solve for these. Once again, I'm graphing this. I'm plotting these points. And then 2, and then I'm also going to have 4 here. So I'm going to go ahead and just plot these points. Okay, so my very first plot point would be negative 1, 1/2. I'd have 0, 1. I'd have 1, 2. I'd have 2, 4. Okay, so here's the thing though. To actually graph my y equals log base 2 of x, because they are inverse operations of each other, okay, what I'm going to do is just reverse these. So I'm going to go ahead and just swap those columns so it looks like this. These are my new plot points. So what I'm going to have is go over 1/2 down 1, over 1 up 0, over 1 up 0, over 2 up 1, and then over 4 up 2. Okay, so this right here is actually the basic shape of a logarithm. So what you can kind of see is it's a reflection of this y equals 2 to the x graph. It's a reflection over a diagonal line here. So this right here, it's kind of something that quickly increases and then it kind of tapers off as x approaches infinity. So what I will have us do is look over these pieces and characteristics of the logarithmic graph just like we did for the exponential graph. When we have a log base a of x, and a is some sort of number that's greater than 1, the domain of this thing, let's look at it. What we would have is the domain before was all real numbers for the exponential, but the range was limited. Now our domain is limited, and the range extends from however much you want. It can go all the way down and all the way up. So our domain is going to switch now, and it's going to become from 0 to infinity, because you're going to notice you couldn't actually plug in negative values for our x. Our range is going to be from all real numbers, so it's going to be from negative infinity to infinity. And once again, you're going to notice between the base 2 to the x and the log base 2 of x, these domains and ranges switched around. The y-intercept, before we had the y-intercept, so actually I have to switch this. Now we have an x-intercept that's always going to be pretty consistent as long as there's no shifts or transformations. So in this case it's going to be always 1, 0. And then the end behaviors, just understand we don't really have end behaviors anymore, but what we do have is a vertical asymptote, because before we discussed how we had a horizontal asymptote for the exponential, so therefore now it's flipped. We're going to have a vertical asymptote. Sorry, I got a little messy here. And then it's right on this line. We're going to get closer and closer to x equals 0, but we'll never get to that line, so it's going to be our vertical asymptote, x equals 0. Okay, so I'm going to do number 54 as an example. Okay, so my tip to you when you're graphing logarithms is to actually graph the most basic function, its inverse. So we're going to be looking at this. This is a log base 4, so the exponential base 4 is what I'm going to use as my guide. So no transformations. I'm not even going to do 4x to the negative 3. I'm just going to be graphing for the x. That way I can easily graph log base 4 of x. So I'm going to do that right now in red. Here's my xy table, and like usual I'm going to choose my negative 1, 0, 1, and 2. So I'm going to get 1/4, 1 always, because 0 is going to produce 1 as an exponential, as an exponent, and then we have 4 and then 16. 1/4. I have 0, 1. I have 1/4. And I'm not going to do my 16. So there's my basic sketch. But now I'm going to graph log base 4 of x. And how I'm going to do that, I'm just going to take those values that I got from the exponential base 4 and swap my xy rows, or my columns. Okay, so this is what I have. I'm going to go ahead now and plot these points. I have 1/4, negative 1, so it's right about here. And then 1, 0, and then 4, 1. So here I'm going to go ahead and sketch this with the dotted line. Here would have been my most basic log base 4 graph. However, now we're going to resort back to those basic those transformations that occur on parent functions. This is my parent shape, and what I'm saying is I'm going to be subtracting 3 directly from the x. So remember, I'm going to flash one of those that slide that has all those transformations on it. But if you add or subtract anything directly to that x, what that is a horizontal shift. It has everything to do with horizontal movement. So I'm going to go ahead and move all of these points that I've graphed to the opposite of what I would think, right 3 spaces. So I'm going to do that in blue. So here I'm going to take this point, move it over to the right 3. Take this point, move it over to the right 3. Take this point, move it over to the right 3, and this is just 1/4, so it's going to be 3 and 1/4. And also what I'm going to do is I'm going to shift that asymptote that was on x equals 0, and I'm going to shift it to be on x equals 3 now. So I'm going to get closer and closer to that asymptote but never cross it. And here we have it. So this actually asks for your x-intercept. So my new x-intercept, you can actually see it visually, but just know that it was this point shifted over 3, so you could just add 3 to that original 0, 1, or I'm sorry, 1, 0. So my x-intercept is going to be at 4, 0. Okay, the new asymptote, the new vertical asymptote is no longer at x equals 0, but at x equals 3. And I think that's all they asked for. Oh, and the domain. Okay, and then so the domain happens anything to the right of that asymptote, so our domain is going to be 4, to infinity. Done.